Hello and welcome all to There is More Than a Mouse, how to truly integrate your app on the desktop. In the next 40 or 45 minutes, we'll be covering 4 topics. The first one is what's the desktop anyway? After that, I'll be introducing you to 3 unique desktop features or concepts, if you will. The first one being menu bars. The second one, how to manage multiple windows, and we'll be closing the talk with file associations. My name is Thomas Künneth. I've been doing Android apps since 2009, and before that, I was doing a thing that's called Java Enterprise. So if this term is not familiar to you, don't worry about that. It's been a while, but maybe some of you have been around for that time, so please raise your hands if you know what enterprise Java beans are. Ah. I've been doing enterprise Java beans 2.0 and doing a lot of Java Swing programming, so that's probably why I am still addicted to the desktop. Along the way, I did a couple of apps and I've also done a few books. So if you want to learn more about me and my work, kindly visit my homepage to get an idea what I've been doing through the years. So let's start with the question, what is a desktop? Now, if you look at this picture, this gaming PC obviously is sitting on top of a desk, so it's safe to say this is a desktop. How about this one? I mean, this device is also sitting on top of a desk, but we are calling it a laptop, and we are calling it a laptop for a reason. So is a laptop a desktop too? And then there is another meaning of the word. Back in the 1980s, there was even an app that was called desktop. The screenshot you are seeing here is from an application suite by a company called Digital Research. It was called GEM, the Graphics Environment Manager, and the app you are seeing here is called the desktop. So you all now know that neither did Apple invent the term app, and it didn't also invent the graphical user interfaces. That happened earlier. The 1980s saw the rise of the graphical user interfaces. Again, a little bit of computing history. In the early 1970s, small computers, which we called home computers, came into light, and they brought the attraction of computer science to many young folks, me being one of them. They were very incapable with regards to processing power, graphic sound, so they were basically incapable of anything doing serious, but nonetheless we had fun. And in the 1980s, these home computers got way more powerful. They became 16-bit machines, one of the famous ones being the Apple Macintosh, the Atari ST, and the Commodore Amiga. What's interesting about them and why I'm mentioning them here is they all had a graphical user interface built in. If you already had a computer by then, you could also buy a software package that provided a graphical user interface. The obvious one being Microsoft Windows, then 2 pretty, well, not too known ones, GeoS for the Commodore 64, and Digital Research GEM, which, like I said, was also available on the Atari. Now, if you look at the screenshots of these graphical user interfaces, they seem to be wildly different, some of them being a little bit more alike the other one. Can you guess which one Microsoft Windows 1.0 was? That's the one in the upper left corner. Sorry to say so, but it doesn't look graphical at all. Anyway, Windows has come a long way. But what all these things have in common is a couple of shared ideas or concepts. So they all had windows, they all had icons, they all had menus, and they all had pointers. And keep this WIMP thing in mind, because that's a key element. All these graphical user interfaces were implementing a thing we call the desktop metaphor. That means interacting with familiar objects like files and folders, file cabinets, trash cans, and printers. Now, you probably are going to argue that these days we surely don't use file cabinets anymore. While that's certainly true, file cabinets were pretty common in the office environments in the 1980s. So these symbolizations of objects were pretty common by the time. And the revolutionary thing was that we were interacting with these objects through an input device that's called the mouse, and this mouse in turn controlled a thing that's called the pointer, and we used that pointer to do something with these objects. And the last thing I want to mention here is these graphical user interfaces focused on documents. These documents were visualized in windows. You could have more than one window at a time open. You can resize that window. You can move it around. You can arrange it the way you want it to. Now, it would have been strange if these graphical user interfaces had invented these concepts independently from each other, and obviously that's not the case. Again, back to the 1970s, a very famous research center, the Palo Alto Research Center, created a workstation that was called the Xerox Alto, and this was the first workstation that had a graphical user interface. You can guess some of the user interface from the pictures you see on the slide. And this was, if you want to put it that way, the first implementation of these concepts you saw for the other user interfaces. Now let's fast forward 40 years or something like that. These screens have gotten even bigger. We have way more colors, but the core concepts still apply. We still have windows, we still have icons, we still have menus, and we still have pointer. So to answer the question, what is the desktop? Actually, the desktop are three ecosystems, or operating systems, or platforms, if you will, and they all adhere to the WIMP user interface. The desktop is usually be used in combination with large screens. We have a mouse and keyboard as primary input devices, and we want to work with files or documents rather than apps. And this is, if you come from mobile development, this is probably one of the most important differences. The user is used to launching an app and doing something in the app. Now the desktop works entirely different. You don't want to decide, hey, I want to do something with Word or Excel. You usually want to work with a file you have created in the past, or you want to create a new file. So not the app is center stage here, but the document type is. Writing app for the desktop, it's basically the same as we know from the mobile space. We can do it using native frameworks and tools with all the benefits and with all the problems and pitfalls we know from the mobile space. And we can use cross-platform frameworks or runtime environments. Why am I stressing the word runtime environment? That's because you probably know one of the most famous or one of the most widely used runtime environment. That's obviously Java. This may sound a little uncommon, but it's fair to say that Java has been one of the earlier ones, and on the other hand, one of the most widely used cross-platform frameworks. Because Java got famous for its write once, run everywhere paradigm. And that's basically saying, hey, I'm doing cross-platform, isn't it? Oh, that was a little bit too fast. Now, what I'm doing in this talk is I'm suggesting you to write apps for the desktop using Compose Desktop. Now, here we go again. So what is Compose Desktop? Compose Desktop is a framework for building desktop apps using Kotlin and Jetpack Compose. Compose Desktop targets macOS, Linux, and Windows, you know, the three ecosystems or platforms or operating systems I mentioned on the previous slide. And Compose Desktop is part of a bigger picture that's obviously called Compose Multiplatform. And here comes a very important aspect. Compose Desktop utilizes a significant part of the Java toolchain, and apps run inside the JVM. And this is very important. The level of integration you get for your app on the desktop is defined by the capabilities and by the limitations of the JVM. Now, please keep that in mind. So if we are doing Compose Desktop, we are not doing native, but we are doing cross-platform through the JVM as a vehicle or abstraction layer between our app and the underlying operating system. Now, this does come with a lot of benefits. For example, we do get native installers, so we can package our Compose Desktop application exactly the same as we could do with our Windows applications. Would be an MSI installation file, or for the macOS would probably be a DMG, or for Linux being a DEP package or something like that. We do have a seamless Java Kotlin interop, and we can use countless open source libraries in our app. There are, however, some, well, drawbacks or obstacles. If we really want or need to get native, we certainly can do so, but we need to do it using the vehicles of the JVM, meaning to access native libraries, we need to do it using JNI, which has been a Java core technology for decades, and I can ensure you, you don't want to do this. Using JNI is not particular, well, in a way it is fun to use, but you should try to avoid that. Fortunately, the amount of multi-platform libraries we get from JetBrains and from the community is getting bigger by the day, so there probably is a good chance that someone has gone through the pains of using JNI for you already. There is another drawback. The app sizes at the moment are pretty big. That's because of the underlying toolchain Java uses is relying on a thing that's called native image, which basically bundles your application code and bundles the essential parts of the Java runtime. And these things, unfortunately, tend to get big. So you want to use tools that try to make your code smaller as much as possible. And there is another thing. We will need a little bit of good old Java AWT and Java Swing code. So enjoy the remaining slides. You will find a few of these old folks around. Now let's come to the first, well, interaction pattern part. Like I said, one of the key things of the desktop are menu bars. Menu bars is something we don't have in the mobile space. That's probably related to screen size. So let's look at what menu bars are. Now these are menu bars of some common desktop applications, and as you can see from the screenshot, the content of one menu can be pretty big. I haven't counted that, but it seems to be way above 12 or 14. And also the number of menus can get pretty big. That's just because desktop applications used to be way more powerful and used to have way more features than we would expect in the mobile applications. Now, there is a rule of thumb that we shouldn't have more than, say, 10 menus, and to make the experience for your users as smooth as possible, you have the possibility of grouping related menu items into so-called submenus. There is another difference which appears to be a minor difference at first glance. On macOS, we have a thing that's called a global menu bar, whereas on Windows and on Linux, we do have a Windows-specific menu bar. The difference is not as subtle as it may look on first glance, because to show a menu bar inside a window, you obviously need a window. Whereas a global menu bar can be shown even if the application has not opened any windows. So it's perfectly possible on the Mac to have an application that is showing a menu bar, but no windows, whereas this is not possible on Windows and on Linux. And this has implications on how we design our applications, because when you run an application without specifying a launch document, you are usually going to show an empty document window. Which is okay if you want to start working with this empty document, but if you just want to launch the application and then open an existing document, you end up with two windows, the one showing that empty document and the second one showing the one you selected, which would not have been necessary on macOS. But that's the way it is. I just want to mention this because you need to keep it in mind when you design your application. Here is how we create a menu bar using Jetpack Compose, and there are a couple of interesting aspects. Each menu can, besides the obvious title, can have a thing that's called the accelerator, which can be used, at least on Windows and macOS, on Linux and Windows, can be used to open a menu via the keyboard. This is not possible on macOS. What is possible on macOS as well is a shortcut which activates the function that is associated with the menu element without having the menu open. So to repeat, a menu can have a shortcut that is used to open the menu, and sorry, that was the accelerator, and can have a menu shortcut to activate the related function without having the menu open. Now let's look at the code. For now, Jetpack Compose windows are tied to an application window. That's because of the frame window scope that's required for the menu bar composable. As I said, a menu has a title and a mnemonic, and a menu item has also a title, a shortcut, and a mnemonic. Now, I'll give you a couple of seconds to look at the source code, and then you probably will want to ask me a question. What is this? Why do I need to have conditions like this? So why would I want to show a menu only on the Mac, or why would I want to show a menu when I'm not on the Mac? So what's going on there? Before I answer that question, please keep in mind that menus and menu items should follow platform-specific human interface guidelines. I have linked the resources for your convenience, and at the end of the slides, you will see where you can download the repositories that relate to the sample, and where you can also get the slides. Now, one more slide, and then I'll show you why you need the conditions. Fortunately, most of the time on the three platforms, the menus share a lot of the same things. For example, each application starts with a file menu, where you would have something like open a file, save a file, and create a new file or a window, followed by an edit menu, which contains the typical system clipboard access functions, cut, copy, paste, and it is most of the time finished with a help menu, which on Windows and Linux would show you the about dialog. But this is one of the conditions where on the macOS we would not show the about menu here, because it will appear somewhere else. Now, the only difference is that on Windows and Linux, for many menu functions, you would be hitting the control key in combination with a letter, for example, control S to save a file, whereas on the Mac, it would be the command key. That's why I encourage you to have a little helper function, which basically does something like this. So what we always need to create a Compose menu bar is associate a key shortcut to our menu items, and this little helper function is fed with a character, and it automatically detects if the corresponding key should be pressed in combination with the control key, that is on Windows and Linux, or with the command key on macOS. And the second listing I've shown you here, this doesn't look particularly cool, but this is the way we have been checking on which platform our Java application has been running for decades, and that's why even though we now call the operating system macOS, Java still thinks it is called macOS X. So that's just the way it is. Now, finally, let me explain why we need these conditions in the menu bar. The Mac has a special app menu that's created by default, and if you do nothing, you get a nice looking copyright box out of nowhere, so this is created automatically, and this even works with our Compose desktop applications, because all the information that will be presented here is put into our build.gradle files, so the necessary information is extracted automatically, and by the way, this lands in a Mac file that's called the info plist properties file. So this is really convenient. And that's why we want to have a condition that says if we are running on a Mac, we don't show the about dialog in the help menu. We don't show it there because it will be shown automatically in this app menu. If we do, however, want to show the same about dialog on all platforms, we can do that. I'll show you later how we do that. We can also link to a settings dialog on the Mac, but if we want to do that, we need to do something. And the third thing in this app-specific menu is to quit the application. Now, there we can also do something if we want to customize the exit process of our application, and if we don't do anything here, the application just close it. Now, this obviously sounded a little vague, so what did I mean by saying we need to do something or we may not do anything? Here's the code. What I'm showing you here is an app level composable of one of my sample applications, and the code that's important here is we are registering 3 callbacks which will be invoked when either of the 3 menu items in this application menu are clicked. So the first one installs the about handler, the second one installs preferences handler, and the third one installs a quit handler. Now, we will be dealing with this in greater detail, so just keep in mind that we register corresponding handlers by passing in lambdas. And this is how this installation takes place. I created sort of wrapper functions because we need to check if the corresponding handler is available on a particular platform. So we need to check, can I register an about handler or can I register a preferences handler? And it turns out this is the case only for macOS. So don't blindly register the handler, but make sure that you are running on a platform that offers the corresponding handler. And as you can see, this is a good old AWT class. The first version of this desktop class appeared with Java 9, and it was enhanced through the years. But if you think when Java 9 was released, well, that is a couple of years ago. Now let's return to my application composable. As you can see, I'm getting 2 states from a class that I call the app state. We'll be looking at how such an app state class is implemented in greater detail later. For now, that if you are an Android developer, think of this app state class like a view model you would know on Android. I am using this app state class because JetBrains uses a similar concept into their sample code as well, and I thought it would be a good idea to make things similar. And as it is done in JetBrains Compose, we just show corresponding composable as long as the corresponding state has the corresponding value. Here it is a Boolean state, so as long as the two Boolean variables are true, the corresponding dialogs are shown, and as soon as it gets false, they magically disappear. But that's ordinary Jetpack Compose behavior. Now here's the last piece of code in my app composable. We are showing a bunch of application windows through iterating over a list, which brings us to our next topic, that is how to use multiple windows. Now, in the next slides, I will be showing you quite a bit of source code, and to get a better idea what the source code will be doing, I think it's good to show you what the corresponding app does. So just have a look at what's happening on screen. So later on you will be more easily able to understand why the code is the way it looks. So we are running an application, we get the default menu, we decide to open another window, we decide to open yet another window, and now we decide to close the window. And now we do something which says, hey, I want to ask the user if he wants to save his work, and then I decide to close the application. And now we don't just want to close the application, but give the user the opportunity to save his changes. In the first place, we dismissed it, and then we tried to quit the application again. This time we said, no, don't save the changes, and this informed our application, hey, you don't need to save your changes, you can easily quit the application. And now let's look at the source code, which does all the magic. Again, this is the source code I have already shown you, so let's quickly go through it again. We provide an AppWindowState. As I said, this can be thought of a view model if you come from the Android space. We register the handlers that are necessary on the macOS, which open the menus, the preferences or the about dialogues, or initiate the quit sequence. Here we open or close the corresponding dialogues based on the state we gathered. And finally, we open a certain amount of windows which is defined in a list. So let's look at this state class. So as you can see, we just maintain a list of window states. So this is another state you will also be shown. Basically, this window state contains all the information and functionality you need to modify application windows. So here we store a list of these window states. We make sure that upon app start, one window is opened. Please recall I said that this is necessary because if we don't have at least one window open, we won't be able to show a menu bar on Windows and Linux. Here, this is the code that adds an AppWindowState instance. This is really easy. It's just creating an instance of the state class and adding it to the list. And this is the same class. This is the same thing, but just removing it. In the process of closing a window, we need to remove the corresponding AppWindowState from that list. So now let's get to something interesting, exiting the app. Remember that there can happen quite a few things. If you have more than one window open, it might be the case that at least one of these windows has unsafe changes, and we want to inform the user that he may lose work if he doesn't do anything. So that's why we can't just quit our application. So we need to make sure that we inform the user by use of an alert dialog or something like that, that he needs to save his changes. That's why we create this exit function as a coroutine. So the function returns immediately, and then the coroutine does its magic and returns once it's iterated over all the app window states and has done what's needed. So we make sure that the function returns immediately. We try to close the window, and we exit the application only if all the windows have been closed. Now, the next question is what happens when we actually close a window? So far, we are just iterating over a list of AppWindowStates and ask some other class to close that window. I'll show you this code shortly. But before, let's look at the application window composable. As you can see, it gets an AppWindowState, and then it collects a couple of states. We configure the window based on that state. Can't go into too much detail, but it is best practice to show the title of the document in the window title, and if the document has been changed, this is marked accordingly, for example, by adding some symbol like the asterisk or adding a text saying edited or something like that. That's what we are doing here. And here we are reacting to close button clicks. So as you can see, we are invoking just a function inside my AppWindowState. Again, you'll be seeing this code shortly. Here we are showing the menu bar. And again, we show the ask to save dialog if some condition is met. We'll come to this condition in a minute. One more slide before we finally come to the AppWindowState class. This is how we actually show the ask to save dialog. As you can see, it's a good old alert dialog, which has 3 callbacks. One is a dismiss function, which will be invoked if the user clicks outside the alert dialog. And the other one corresponds to 2 buttons, a confirmative button, which would then save the document, and a don't save button, which basically says, no, the user has acknowledged that he has unsaved changes, but he deliberately wants to get rid of these changes. And as you can see here, I am just invoking corresponding functions in my AppWindowState class. And this finally is the AppWindowState class. In that orange bordered box, you see just the implementations of the functions we have been called from the previous slide, and they don't do much besides when I actually need to save documents, but setting a property which is based on an enum. This is the enum that basically says show the dialog, don't show the dialog, the dismiss button has been clicked, the affirmative button has been clicked, and the ignore changes button has been clicked. Why do I use an enum for that? As you will see shortly, it is easy to react to these changes in an asynchronous manner. So I just need to get one state, which is the current value represented by such an enum, and react to this enum state, but it's just one property I need. And this is what is taking place when we want to close an application window. So if unsaved changes appear, we make sure that the ask to save dialog gets visible. Then we wait until that dialog is no longer visible. Remember that this happens when the user either clicks the dismiss button or clicks on the save or don't save buttons. And then we provide a return value that's based on the state, which meaning if the user says dismiss, then the window should not be closed, otherwise the window can be closed. And here you can get a good idea why I use this enum. So handling all these different states is really easy and nice to read through the speaking names of the enum values. This brings us to the last topic I want to discuss. It's called file associations. File associations are unique to the desktop, and the underlying concept has been adopted by the mobile platforms. If you know how intents work on Android, you have a broad approximation what file associations are that desktop are. But again, I'll be showing you a sample so that it makes it easier for you to understand the code that I will be showing shortly. So as you can see, we have double-clicked on an icon which opens the application, and then we click another one, and we always show 3. So here's the third one. That's it. Now let's implement this. The bad thing is that file associations are handled differently on all platforms, meaning it is done differently on Windows, macOS, and Linux. The good thing is that the underlying mechanics are handled by a tool that is part of the Java toolchain that's called the JPackage. So you can basically add command line options to JPackage, which says, hey, I want to have file associations, and an application can have more than one file association. This file association is stored in a simple properties file. As you can see, we need to specify a MIME type. We need to specify an extension, for example, .doc, .html, and things like that. And we need to specify a description. You can also specify an icon. I omitted that for brevity. Now the problem is, as far as I know, and at least in the keynote, nothing else has been communicated, this is not yet officially supported by Compose Desktop. But we can pretty easily work around this. The code you are seeing here needs to run for macOS. Unfortunately, I can't go into greater detail. For reasons unknown, the Gradle plugin that is invoked when building a Compose desktop application writes that info plist file that is essential to any macOS application on its own, which is a sad thing because that same file is created by the JPackage command, which would make adding the file associations way easier. So now that for the moment the info plist file is created by the Gradle plugin, we need to add the corresponding entries on our own, and as you can see, this is how we do it. We just need to specify additional entries, and this is how these entries would look like. You can get an idea from the source code of this application. As I've already said, I'll show you the link to the repository after the talk. On Windows and Linux, fortunately, the JPackage command is invoked, but as Compose Desktop doesn't officially support it, obviously the corresponding file associations command line parameter isn't added, but we can hack that in. So as you can see here, any task that starts with package gets that thing. So this may look a little bit hacky. We might fine-tune this, but I can at least say it works. And hope would be that we get official support from this by Compose Desktop in the future. But it works. Now, what do we need to do in our app code to react to files being passed to the application? As you can see, as any Java application, you can pass command line arguments to the main function. This is obviously the same for Compose Desktop. And we just passed the list of command line parameters to our application composable. What this grayed outline does, I will be showing you in a minute. So as you can see, we don't have much magic here. We just put the list of command line arguments we got from the main function into a mutable state list, and we use the contents of this mutable state list to show the file names, just as you saw in the video. Now, unfortunately, there's once again a differentiation needed between macOS and Windows and Linux. On macOS, we need to register the AppOpenFile Handler because on Mac OS, when you pass a file to the application, this is passed to it through some eventing mechanism, and that's why we need to have this code. On Windows and Linux, however, it doesn't work this way. Again, these handlers just aren't there. And there is another problem. Unfortunately, any passing a file to an application opens another app instance. While this may not sound dramatic at first sight, there is an issue we want to solve. Most applications should also have a window menu which lists all open windows. Now, if each passing command line argument launches a new app instance, obviously this application window menu would always have one entry because it has, well, always exactly one item. So how do we solve this? Here we are doing some clever hacking. What we want to do is, upon start, we just check if another instance of the app is already running. If it is, we just pass the command line arguments our instance received to that other instance and then quit. And otherwise, we just work with the command line arguments we received and make sure that another instance of the app that might be started afterwards finds us. Let's see how we can do this. Here we are utilizing good old Java sockets. So this is really good old-fashioned Java stuff. So what we basically are doing here is we try to open a socket. If that socket exists, we just pass in the command line argument we received, and then we quit. So this is what would be happening if an instance is already running, because that instance would have created the socket, and our instance would be able to feed the command line arguments just in. And this is the code that opens the socket. So if we are the first instance of our application, obviously there is no other instance running. So we just create a server socket, and the server socket will be found by any subsequent instances of our application, which would then pass the command line arguments in, and we would be able to consume it. There are obviously many ways to do this, so using Java sockets is one of the most simple approaches. You could also do some event bus mechanisms, so you are free to use whatever you see fit. But like I said, this is the most simple and easy to use approaches. That's almost it. There is one more thing I'd like to show you. So what happens if we run the application and drag some files in? Now, isn't that cool? The problem is this doesn't work the same way as we would be doing usual command line argument passing. We need to implement some simple drag and drop stuff. Fortunately, with the latest Jetpack Compose versions, this is really easy. As you can see, you just need to use a modifier that's called on external drop, and then pass a callback which just examines the type of data that has been passed, meaning that has been dropped, and then react accordingly. And this is, I believe, really cool stuff. This is the link to the repository that contains the two sample applications, so I'll give you a couple of seconds to scan the QR code if you want to, but I'll also be mentioning the link on social media and also be posting it on my homepage. That's it. Questions, thoughts, comments? Thanks for listening, and please don't forget to vote. Thanks again.